Minesh-shaitanir-rajim. Bismillahir-rahmanir-rahim. This is my lecture, online lecture about the course of thermodynamics having the course code of PHY331. And in today's lecture, I will discuss hydrostatic force depends on the path and work done in thermodynamic description of one-dimensional system, wire, surfaces, and electrochemical cell. The basic objective of today's lesson is to understand that whether the work done in hydrostatic system depends on path followed by the systems. The other part of the lecture is devoted to the understanding of 1, 2, and 3-dimensional system. In one-dimensional system, we will discuss the wire. In two-dimensional system, we will discuss surfaces. And in three-dimensional system, we will discuss the electrochemical cell. And then we need to calculate the work done in changing the length of a wire. The first part is devoted to the understanding of hydrostatic systems, and we need to know whether the hydrostatic system depends on path or not. Here is a PV diagram for a hydrostatic systems. We have the system in equilibrium at initial position and in final position, and the objective of this workout is to bring the system from initial to final. So there are different ways followed. One of the way is the IAF, other way is to bring the system through IBF, and the third one is to directly take the system from I to F. We need to calculate the work done in three different ways, in the three different paths, and then compare whether the work done is same or different from each other. The configuration of the system can be described at the initial position, that is I, by PI, VI, and TI, and the system at the final position could be described by the thermodynamic coordinate PF, VF, and TF. So the first way to bring the system from first equilibrium state to the second, the final equilibrium state, is followed by the way that is called as IAF. In the first step, we need to IA. This step is further divided into two steps. One is the I to A and other is the A to F. From I to A, we need to keep the pressure constant, and this is called as isobaric process. And from the second A to F, we need to keep the volume constant, and this is called as isochoric process. So the whole work done in these two steps is given by minus 2 P naught V naught. That is actually the area under the line IA. So the other possible way is that we need to take the system from I to B and then B to F. So what happened? The work done in this route is given to be minus P naught V naught. And the third steps to bring the system from initial position I to the final position F, the work done in this case is equal to minus 3 divided by 2 P naught V naught. So if we compare the work done in the three different paths, so it is clearly observable that the work done is different from each other. So it means the hydrostatic systems depends on path followed by the systems. So if we can generalize, the work done only depends on the work done not only depends on the initial and final state of the system, but it also depends upon the intermediate states. In other words, it depends upon the path of integrations. So the equation for quasi-static process cannot be integrated until P is specified as a function of V. So the work done could be generalized as minus integral Vi to Vf P dV. So there is difference between the infinitesimal amount of work and other infinitesimal values that are actually the dP and dV values. The hydrostatic work dW is inexact differentials. So dW is not differential of exact function of thermodynamic coordinate, because work is not a thermodynamic coordinate. Different interpretation that the work is inexact differential is that the first one is that the work is path dependent integral, as we have proved in the last slide that work is a path dependent integral. So it means work is not a state function. There is no function of thermodynamic coordinate representing work in a body. The second interpretation is that the physical interpretation of thermodynamic work is that the performance of work is an external activity or process that leads to change in the state of this body. It means it needs to change the energy of the systems. So it means the representation of work in a body has no meaning. So work is actually not a quantity that itself moves, but it is a process that moves another quantity, that is the energy of the systems. So if we can compare the exact differential of work in mechanics and inexact differential in thermodynamics, so we have some basic points in that. In mechanics, the forces are usually depends that actually only depends on position, but in thermodynamics, the pressure not only depends on coordinate of volume, but it also depends on temperatures. So the calculation of work in thermodynamics is path dependent unless other conditions are applied, such as isothermal process in which temperature is constant, or adiabatic process in which some other coordinate are kept constant. So in that case is possible, but in general case is not possible. So we have the other part of the lecture, that is work in changing the length of a wire. So we consider a one-dimensional system and we need to calculate the work done in changing the length of a wire. So for that purpose we need to consider a wire having a length L and tension in the wire is represented by tau. The length is changed by infinitesimal amount dl by an external force equal and opposite to the tension. So the work done is given as dW is equal to tau dl. So the tension tau is a function of length and temperature as it is shown in the above equations. So positive value of dl describes the increase in length, which is a positive work, and the work done for finite length is for finite change in length is given by W is equal to Li to Lf tension dl. That is actually the final. So it means when the wire is undergoing a motion due to large unbalanced force, the integral cannot be evaluated in terms of thermodynamic coordinate. We need to refer the whole wire in that particular systems. So this is actually the work done in bringing the system from initial to final position, or changing the length from Li to Lf, that is equal to the integration of the tau dl. So the other is a two-dimensional system, and that is work done in changing the area of a surface film. So for that purpose we need to consider an area of a soap film that is consisting of two surfaces. Here in the figure is shown, this is the area of the figure and the length of that the area of the soap film, and its length is represented by L. So soap film consisting of two surfaces enclosing water stretch across a wire framework. So look at the right side of the wire framework. Here it is movable. I mean we can move through some distance dx. Here infinitesimal, it has been moved by infinitesimal distance dx. So consider the length of the movable wire is equal to L, having surface tension in one surface is equal to represented by gamma. So the external force acting on both sides is equal to 2 gamma L. And what happen when there is an infinitesimal displacement dx, then the work equation could be written as very easy: force multiplied by dx. So dw is equal to 2 gamma L multiplied by dx. If we consider that we have two films and the area for that is equal to 2L dx is equal to dA, so it will be very simple, and the equation for work will be equal to dw infinitesimal work done will be equal to gamma dA. The surface tension is measured in Newton per meter. So for finite changes from an initial area A to a final area AF, the work equation could be written as W is equal to AI to AF gamma dA. So what happened? The process may be considered as a KUST by maintaining the external force at all times only slightly different from the force exerted by the film. So we have a third system, that is the description of some electrochemical cells and in work done in moving a charge within through electrochemical cells. So electrochemical cells are actually used for storing energy. So how we can move when these electrodes of the electrochemical cells are connected to a resistor, so current will move through the conductor. So what happen? The charge is moved through a distance, and we can measure the work done in this case. So the motion of positive charge from a region of high electric potential to a region of lower electric potential, that is actually called as the conventional current, is normally defined. So electrochemical cells is being represented by an EMF that is connected to a variable resistor. So the external potential difference may be made equal to or slightly less or slightly more than the EMF of electrochemical cells by means of variable resistance. When there is a difference between the electric potential, current will flow through the conductors. So by setting the external potential difference infinitesimally smaller than the EMF of the battery, what happens? Some charge dz will flow from positive to negative terminal of the battery. So as a result of this motion of charge, work will be done. So the work is again of two types. Work is done by the cell on the resistors, or work is done by on the cell. Work is done on the cell by resistors. So in the first case, when the external potential difference is made slightly larger than the EMF of the cell, charge will move in opposite direction and work is done on the rechargeable cells. So we have again positive and negative work done in this case. So the amount of work done in both the cases, whether it is positive or negative, that is equal to dW is equal to epsilon dl. Here we can see that if the work done is in such a way that the potential difference, the outside potential difference, that is actually the external potential difference, that is made infinitesimally smaller than the EMF of the battery, then as a result of that, some charge will move across the conductor and the direction of the charge will be from positive to negative terminal of the battery. So in this case, the battery will lose the charge, the charging. So what happened? Work is done by the cell on the resistor. So it means it is the negative work is done by the system on the surrounding is the same like work is done by the system on the surrounding. So in this case, work is done by the cell on the resistor. So what are the consequences of this work? If this work continues, the charge of the battery will reduce and a time will reach when the battery will, the charge of the battery will vanishes. So this is one type of charge, the motion of one type of charge in this particular circuit. What happen if you want to recharge the battery? We need to connect the same battery or the same terminal of the battery with the external potential difference. But keep in mind, in this case, the external potential difference is different from the internal potential difference or EMF of the battery. The external potential difference in this case is made slightly larger than the EMF of the cell. When it is larger than the EMF of the cell, what happens? So charges will move in opposite direction and work is done on the rechargeable cells. So the charges that was setting move in the first case in one direction, that will move in the opposite direction. So what will be the consequences? The work is done on the rechargeable cells, and as a result the battery will not losing charge, otherwise it will gaining charge, because the external potential difference is higher. So this is actually the charging process of the battery. So this is actually the work done in both cases. In first case the work is done by the cell, and in the second case the work is done on the cells by the external potential difference. So we have the work done, but anyhow the magnitude of work done in both cases is same, and it depends upon the EMF of the battery. And dz is actually the magnitude of charge, that is the actual amount of charge that is moved through the circuit, and z represents the state of charge of the cells. E is again the electromotive force, is epsilon. So charging the cell require positive dz, this is called as positive dz, and work is done on the cell to increase the concentration of reactants. In this state, work is done on the cell to increase the concentration of reactant, while negative dz represents the direction of motion of charge in the external circuit. So in this case work is done by the reacting chemicals on the surrounding, so that is called as the negative dz, and in this case battery will lose the charge. So if we can calculate the work done in this case for finite amount of z, the work done is written as, if we want to find out this charging from initial to final states, then work done will be equal to integral zi to zf. Zi is the initial state of the battery and f is the final state of the battery, epsilon dz. Epsilon is the electromotive force and dz is the infinitesimal, or the amount of charge that is moved through the circuit. So in practical application the current I is measured instead of charge Z. If we see in most of the practical application we cannot see the magnitude of set or charge in a system, otherwise we measure it with the help of some other notation, with the help of some other physical quantity, other quantity, that is the current. So we can express this equation W is equal to Zi to Zf epsilon dz, that is presented in form of dz. We can convert it into I mean that is actually the current, because we have some relationship between the current and the charge. Actually I, or the current, is equal to dz divided by dt. This means that the charge moving through a conductor per unit time. Di is equal to dz divided by dt, the amount of charge moving through a conductor per unit time. So if we do the cross multiplication, what happens? The dz will become equal to I dt. I mean we have done just a cross multiplication, and I is equal to dz divided by dt is converted into dz is equal to I dt. So what we need to do, we need to put the value of dz over here in this equation, and we need to modify. Similarly we need to change the definite integral as well. So this equation could be written as the motion of the charge, the charge particles moving through the external circuit to charge the battery or discharge the battery. It can be written as, the work done could be written as W is equal to I to F epsilon I dt. So this is the amount of work done in charging the battery and discharging the battery. So here we can easily see that current is a measurable quantity. We can easily measure the magnitude of current through the conductor. And electromotive force is also a known quantity. If these two values are given to us, and if we know the final and initial position of the systems of the electrochemical cells, we can easily find out the work done in charging the electrochemical cells or discharging the electrochemical cells. So in this case we actually concentrated on the work in moving charges with an electrochemical cells. So this is actually three-dimensional systems. So actually in this lecture we had discussed the work done in changing length of the wire, work done in changing area of the surface film, and finally for three-dimensional system we discussed the work done in moving charge with an electrochemical cell. So that is actually the charging discharging process. So this is something about today's lecture. So I hope we can discuss some we can move forward in the same chapter toward new topic in the next lesson, inshallah. Thank you very much.